Okay, so this is what we did. It's showing too much of me. This was the homework last week. Any success?
I got most of the way through it. I kind of did it at the same time I did all the formulations for, you know what, you were correcting it on Friday. So as you can see, most of the stuff would have gone wrong as well. I did try to correct it.
Did you have a look at it? That's okay. Right, so the first question is that's simple. It was just introducing a limit of 50 on the amount of inventory, which translates very easily to a limit on the inventory all the time. And the second formulation is more or less just practice of the standard model that we were looking at. So there's nothing.
3.
Okay, so there are two solutions, optimal solutions, which I found. And so one of them is produce all the airplanes at the beginning, in the first quarter, and then do nothing. And the second one is to do 5 in the first quarter and 5 in the third quarter, and do nothing in the second quarter. In both cases, you get the same cost. So, did you get 2 marks?
I didn't. My constraints were broken, so it wouldn't work.
Did you get any marks?
I've had an incredibly bad weekend, so.
Okay, so you don't get any more.
Sorry.
Never mind. I get all the marks.
That's all that matters.
I get all the chocolate in the end. Okay. So today it's called, what is it called? What we can do today. And then
Just one.
There we go.
okay. What does it say? Batch planning. We've been doing batch planning, and we've been doing a mixed integer programming model. Mixed integer programming is a very powerful technique. It can solve any problem. Well,
To an extent.
It can solve many different problems. But sometimes it can be slow if you have large problems. And so the motivation to do a different algorithm is that this one is probably fast, in the sense that it's captured by polynomial time. Does it say anything to you?
Like trains, for example.
Trains are not polynomial time. No. Anyway, so okay. So if it's not saying anything to you now, wait for another half year. Come exam time, it will have to do. Right, but the dynamic algorithm can only be applied if you have leading functions. Okay, so it doesn't work if you're mixing different products on one machine, like we have these constraints between how many magnets of type 1 and 2 you can make all together, things like that. It doesn't work if there are some limits on how much you can produce in any given period. So you have to be able to, pardon?
Like using the hours and stuff.
Yeah, like that. Or using storage. A limit on storage. And you want to assume that the initial inventory is nothing, but that's okay. But these two assumptions are crucial. And And these two assumptions, so let's have a look at the homework solution. So I'll just write the homework solution. There were two possible solutions. Okay, I'll try to make a table. So period T, there were 4 periods, 1, 2, 3, 4, and there was another solution, 1, 2, 3, 4. And the demand was 3232. So this was the airplane's problem. Okay, and the solution we got, xt, it. Okay, so the first one was to, well, I promised you that it was an optimal solution. You may or may not believe me, but it was to produce 10 in the first period and then nothing. And the second one was to produce 5, nothing, 5, nothing. Okay. And then, what's IT? You have enough information to know what the inventory
That
is.
was the inventory passed over.
7, yeah. 5, 2, 0. Just looking in
Read upside down.
7, 5, 2, 0. Yeah, it's a necessary skill to be able to read that because of the projectors. Okay, and the other one is 2, 0, 2, 0. Yeah, so that's the number of airplanes stored at the end of each quarter. Okay, if I make 10 and sell 3, I'm left with 7. And so on. What's this one? Now, both of these solutions have this exciting property that you only produce once you've run out of everything. Okay, so you don't produce while you still have something in storage. And consequently, the amount you produce is the amount that exactly covers a certain number of next periods. Okay, so in this example here, you produce just enough to cover quarter 1 and 2. And here you produce just enough to cover quarters 3 and 4. Okay, and in this optimal solution, you produce just enough to cover the next 4 periods, including the current one. Does that make sense?
Yeah.
Now, under these assumptions, you will always get an optimal solution that looks like this, as these properties that I've just described. Thank you. Okay. No, I don't think. Okay, so I say it again. Okay, the property of these solutions is that you produce exactly the number of things, the amount of products that covers a certain number of periods exactly. Okay, so in this case 4, and in this case 2 and 2 again. And you don't produce while you still have something in storage. Okay. Now, when you look at this, Well, first of all, if you moved, for example, one from these 5 produced in Q3 to Q1, then that increases the cost because you have 3 in storage, 1 in storage, and you're not saving any setup costs. Okay.
It's like 2 million something, wasn't it?
So you don't want to produce, you don't want to have something still left here when you're starting to produce something again. Okay. I'll call it a lemma. Can you see what I'm writing? I'm not writing anything yet. So there is a lemma. It does show on television. The guys who realized this were called Wagner and I don't know, Witten or Whiting, apparently, in 1958. And they realized that there exists an optimal solution which satisfies number 1, the production only takes place when stock is 0. Okay, so that means that in mathematical notation it's this, but what it means is that production only takes place when stock is 0 or inventory level is 0. Okay. So if you still have something left over, so this is non-zero, there's no production. And number 2, okay, the amount produced when production takes place is equal to the exact amount you need for a certain number of periods. Okay, so so for any t, if there is some production, so if xt is greater than 0, then there exists okay such that the amount produced in this period is exactly the amount of demand in periods t, t plus 1, all the way to t plus k. Okay. Does that make sense? Okay, this is the important bit, and this follows from that because, so if you want to prove it, proof, approximate proof. So I'm leaving out all the details. And where am I? Okay, so the first bit, if you, so okay, so the idea is, it's not really an outline, it's just an idea. So suppose for some t, it's not 0, okay, so that means that both xt and it minus 1 are non-zero. And, well, induction means, proof by induction means, what does it mean?
Proof.
Take
And then add them together.
the least such k, such t. For all smaller t, this is 0, the product. Well, base case, yes, base case is then t is not the first period because by assumption, what was one of the assumptions?
No, starting inventory has to be 0.
Exactly. So I0 is 0. Okay. Therefore, also I0 times whatever is still not. Okay.
Is that I0 or IT? Yeah, sorry.
That's a 0.
Yeah, thank you.
So that was one of the assumptions. Okay. And then the idea is that so t is something great. So in particular, there has to be some period, previous period when we produce. So there is a when we produce something before the current period, because the current period is not the first one, just proved. And, well, we can sort of assume that the demand is non-zero in every period as well, but okay. These little details I'll just ignore. So if we, but there is no reason. So if now we can decrease the production in that previous moment by IT minus 1. Okay, this is kind of complicated. It's not so complicated. And increase xt by IT minus 1 and still get feasible solution which has lower cost. It's not very convincing. Okay, so I'll do an example of what I mean by this. This is the Q, this is X, and this is the inventory. Okay, and your demands are 5, 2, 7, 3. And you decide to produce, for some reason, you decide to produce 8 here, and then nothing there. Okay, and then 9 here, and nothing there. Okay, what you have left in inventory is 3, is 1, is 3, is not. What you can do instead, and do better, is, what does it say, decrease this by 1. Okay, so this will go down to 2, this will go down to 0, and increase this by 1. And you get a better solution. And it's better because there's no extra setup, so the setup cost doesn't go up, and there is less storage cost. So this example illustrates what's meant by this idea. So if it ever happens that you're producing something, and there was, looking at black numbers, producing something, and there was still something left in stock, then why not produce it today rather than having kept it from before? Okay. Because then that decreases in storage cost and doesn't increase any other storage cost. Now here we're using the assumption that there's no limit on this, because essentially we couldn't increase it if there was a limit. So
Actually, really.
Very useful things like retail.
Yeah, oh, definitely. Definitely.
Oh,
knowing mine and yours jobs, they don't think like this, kind of.
buy it in bulk.
Yeah.
Oh,
Get it next week. We'll just get to it.
Yeah,
Okay.
I was looking at it was in the next couple of weeks. It's just like, why do you do that? You're never going to sell it.
This is Christmas, that's why.
We're going to never sell that much.
Exactly. Yeah, just skip.
So you end up with that problem of
Yeah.
having stuff in storage and then they buy more for the year after. And then you just end up with an endless amount of storage.
yeah, I think that's a managerial problem rather than a mathematical.
But it's still part of that problem. That's the solution to a lot of people's problems.
Yeah.
All right. Any questions about this bit?
No,
Makes
crystal
sense.
clear, to be honest.
Good. So then we to then prove the 2, but that follows easily from 1. Because what 2 says, I'm too lazy to go up to show it again, but 2 says that the amount you produce is the exact amount you need to cover. You need to cover a certain number of periods. Okay, and that is obvious because what you want to do is end up with 0 inventory. So if you want to end up with 0 inventory after a certain number of periods, then what you do is produce exactly enough to cover those periods. Okay. Right. Now, so this lemma is behind the idea of a dynamic programming algorithm for this. Now, what is a dynamic programming algorithm? You've been doing it with Philip, so you know that.
We've been doing it.
With Philip, dynamic programming.
Oh, God.
Sometimes these connections between different bits and pieces of what you're learning. Okay. We're running out of time. Oh, interesting. Okay, so to me, a dynamic programming algorithm is really just looking for the shortest path in some graph. Just not like that. The first example I think Philip did in the lecture was that you can have a dynamic programming algorithm, or dynamic algorithm for the shortest path in a graph. Okay. But that's not an example of an application, but it really is the substance of dynamic programming, is that you're doing shortest paths in graphs. But they have, but they're somehow special graphs because they're directed and they don't have any direct cycles. So you're just always going kind of from left to right or from right to left if you prefer. It doesn't really matter from top to bottom. So you're just going one direction always. Okay, and they also come in certain layers. Yeah, so in dynamic programming, I don't want to draw it on this because it's. I'll draw it on the whiteboard.
Like that?
As an example. Yeah, like this. Okay. I'll just draw it. Okay. Oh no, it's you. That's okay. Approximately. Okay, so but the graphs that you're looking for the shortest path in, they usually cut some stuff. Yeah, some starting vertex, and then have a number of vertices, like a second layer, a number of vertices, a third layer, a number of vertices, last layer. Usually you have just one vertex at the end, and you have some arrows. You go forward like this, or maybe some more forward than just one layer. That's roughly what goes on in there. So the graph, and then you have some kind of some cost on each of the arcs, the edges. And you're looking for the shortest path from left to right. You're looking for the shortest. Then you break. Okay, so the total cost is equal to the sum of the costs on the edges, and that's what you want to minimize. Okay, now so in dynamic algorithm patterns, these vertices, vertex or node, is called a state. Does that sound familiar? What's wrong?
Stage, nothing.
Yeah, and each of those layers
Stages and stages.
is called a stage. And then you have some kind of and which outgoing edge you choose in every state, that's decision in the dynamic algorithm. Right?
Mm-hmm.
So that's basically what any dynamic algorithm is. And then there's some kind of recursive formula which more or less tells you that the best you can get here is minimum of, well, you look at all the incoming edges, and so best. So this is state n. So best possible cost in n is the minimum of. You look at all the predecessors. This was predecessor k, and you look at the best possible cost in that predecessor plus the cost of the edge going from that predecessor to n, and it goes on all arrows that go from k to n. Kind of. Look at all possible arrows that can take you here, and you add whatever is the best for that previous node with the cost of that edge. That's the idea of dynamic programming, and then kind of whether you do it going forward or you going backward, but that's essentially the idea.
No, it's tired. I look tired now.
Yeah, okay,
Sorry.
that's okay. So, okay. Okay, this is I just wanted to demonstrate. I'll just demonstrate something else.
Everyone looks so much fun.
Okay, so in this dynamic, for this problem, the graph is kind of simple because you have for each of the periods you have a node, and then you have some terminal node T. Okay, so there is one node for each period in the time horizon. Maybe I shouldn't call it T. Maybe I should call it hash as end. In the time horizon, I don't want to call it T because T is the time horizon. So we have n periods and a terminal node. And in this case, each node is its own stage. Maybe I'm not saying it quite well, but maybe you should start like saying that there are exactly as many stages as there are periods in the time horizon plus terminal stage, and maybe that's not even called stages. And each of the stages has exactly one state in it. So that's the idea. So exactly one state. In each stage. And you have all the forward arrows. All of them. So I've got 2 then missing, but you get the idea. I'll put it there just to make sure. Now the idea is that when you found your shortest path, the vertices or the nodes on the path correspond to the periods in which you're producing. Okay, so you always have to produce in the first period. That's where you're starting. You always have to produce because you're assuming non-zero demand. I didn't say that for you. You're assuming non-zero demand, and you're assuming 0 inventory at the beginning. Okay, but then you decide for how many to produce. Okay? If you're producing only for now, you jump to 2. If you're producing for now and next week, you go to 3. If you're producing for now, next week, and week after next, you go to 4. And so on. Okay? And so all the vertices that you visit on your shortest path are going to be the periods in which you do a setup and produce something. So the node on the shortest path from 1 to hash correspond to periods where setup. So xt equals 0. Okay, and the amount to produce is, well, we know what it is. Right, we've seen this formula before. So you have to add, I'm going from t to some t dashed x, not x, but q I. Okay, so this is what we call xt. So t dash, what is t dash?
The one before T.
That's what it was before, but now it's the one after, confusingly. And so you're saying, well, okay, I'll put t dashed minus 1.
Okay.
So t dashed is the next period we've set up. So the next which is the same thing as the next node on the shortest path. Okay, so maybe I should say that dash is n plus 1. Like dash is n plus 1, because otherwise I don't have a way to work out what hash minus 1 was. Okay. So for these purposes, hash is n. Maybe I should have called it n plus 1 to start with. And it's special somehow, so I don't want to give it a special name. Okay, now the last thing that is missing is the cost on the edges. If we know the cost on the edges, we know how to solve it. Yeah? So what is the cost on the edge going to be? So which edge do you want to look at?
The shortest path.
No, because you don't know what the shortest path is first. So you just want to look at all the edges.
So we look at the one furthest right, where our end goal, and move backwards.
At the very
Yeah,
end.
no, I'm looking at all the edges. So let's say I want to look at the edge J to K. Okay. So what is the cost of J to K? Well,
C.
C. Okay, C, J, K. So the cost of transition, as it's called in dynamic programming language, from state J to state K, is, well, you have the setup cost. What did we call the setup cost last week? Was it G or was it A?
That's the one. G.
G?
No, A.
A?
Yeah, A. In the front page.
A, so this is the setup cost.
Yeah.
The G was the stock holding cost.
Looking at the wrong page.
So that's coming next, okay? So we've got A. That's the setup cost. So this edge is accounting for the setup in period J. But now you want to account for the storage cost of everything from period to storing until period J plus 1, J plus 2, all the way to K minus 1. Okay?
Okay.
So now the storage cost is, I'll have to add them all together in the end. And I'm going from J plus 1, because there's no, yeah, to K minus 1. Okay. So what I'm doing is, next, so now it's week J. So I'm producing something, and I'm producing all the products that I need for periods for this week, next week, and so on, all the way to K minus first week. And in week K, I will produce again. Okay, that's the idea of the edge J to K, transition state J to state K, given that. So I'm looking at the cost of storing things for next week, the week after, the week after, the week after, and all the way to week K minus 1.
Wouldn't K minus 1 always be 0?
Why should K minus 1?
When you have no storage, shouldn't it be J to K minus 2?
Oh, why?
Because when you're in the final month before you start producing again, shouldn't your inventory be 0 at the end?
You don't start producing if your inventory was at 0.
That's
So
what I'm
at
saying,
K
so the
minus
month
1.
before you start
No.
producing again, shouldn't it be 0?
Then once K minus 1 is 0, the week after, that's when you start producing.
K is
That's what I'm
0.
saying.
Yes, well,
I'm just going off of when you did these. That's what I'm
no.
saying.
Okay, so this is not going to, no.
Slightly different. Okay.
That's why I'm only going to K minus 1, not K. Okay, because I'm not keeping anything until
Yeah, that's
K.
what, that's what we're saying.
It's just the indices are one off from what you're thinking. That's the reason why K minus 1 is.
No, I understand the K minus 1. I was just saying, but when you go to K the month after it, shouldn't have K minus 1's storage been 0 anyway?
Yes,
So you don't really need it.
I do, because I have the indices shifted by 1. Okay, it'll be obvious now. QI,
Yeah.
Mm-hmm.
okay, that's what I need to keep until that period, because that's the demand.
That's fine.
Yes, so you need the K minus first.
Yeah.
You don't
Otherwise
need
it
the
would
K's.
Yeah.
Because the K is what you're going to produce afterwards.
Mhm.
Okay, but the K minus first you need. But you have to multiply it, well, you have to multiply it by G to start with, so put the
Little
G here.
GI. Little GI. Oh, then there.
Yeah, in fact, I could, I mean, yes. You could have different storage costs in every period, but let's not overcomplicate it. And let's just say that the storage cost is the same. But you could have a different storage cost.
Yeah.
I think.
Why not?
Did you not?
Why not? No.
Maybe you couldn't, I don't know. Scratch it.
It needs to be cold and it's in the
Remove this. Okay, let's say I'm a bit in time pressure, so I wanted to do the example with the airplanes. Oh dear, I think we'll have to come back to this next week and do the example. Okay. But okay, because I've been doing this theory, I should show you the example. Yes, what am I multiplying it here by?
Cost.
No, the length of
I
storage.
was just talking about.
Would it be something? This can sound stupid, maybe hash minus 1.
No, it would be I minus j underneath.
Oh, for the period of one.
And so this is how long I keep that amount for. So when I is next week, j plus 1, then I keep it for 1 week. When I is the week after, j plus 2, I keep it for 2 weeks. When it's k minus 1, then it's k minus j. So that's the length, the number of weeks, work periods, that I keep that amount for if I make it today. So add it all together, multiplied by the unit storage cost, add the setup cost is going to give you the transition cost, and then that recursive thing is that recursive formula. I'll just write it and then there I stop. Okay, so I think it's usually F in village notes, isn't it?
Is that an FLA?
Yes. That means formula.
Oh, formula.
It does.
Never seen that notation.
Every day you learn
Every day I
something
learn
new.
something new.
I go back to them.
Like
So for
29 grams
For
of
any
nothing.
t, this is the minimum of fj plus the transition cost from j to t, and I look at all the j that are less than t, so all the states to the left. Except I have to start somewhere, right? So F, so F 1. So I don't know. No. Okay.
Yeah.
Sorry. It was time pressure. I apologize. I'll do this properly next week.
Good shot. Right, okay. Yeah.
Because it wants me to do it from the back. Okay, so I'll do it properly next week, and that also means that the homework I've given you should keep for next week. Okay. Sorry about this. Just run out of time.